Both simple and combo gear trains have the restriction that their gear shifts must rotate in barriers fixed to the frame. However, this is a requirement that limits the versatility of the gear trains. If one or more lane shifts rotate around another shift, as well as spinning about their own axis, the gear train is called a planetary of an epicyclic gear train. This adds design flexibility and permits very compact gearbox with high reducing ratios. Because they are basic devices with multiple degrees of freedom, they are used in automatic transmissions for automobiles and trucks. For example, this picture is the planetary gears in automatic transmissions. A clutch is a mechanical device that engages and disengages power transmission, especially from the driving shifter to the driven shifter. So we can use a series of clutches to control the speed and get the speed we need. This video displays the automatic transmission and how it works. You can also watch this video on YouTube. A simple planetary driver is shown schematically in this figure. Planetary gear trains are typically made up of the following. Some gear, it may or may not be fixed. One or more planet gears are mounted on the movable arm of carrier, which itself may rotate relative to the sun gear. And the internal ring gear, sometimes it is not used on planetary gear drivers. The symbolism used to represent planetary drivers is also shown in this figure. Symbol S is for the sun gear, P is for the planet gear, R is for the ring gear, and C is for the carrier. It allows the designer to represent the structure of the planetary driver simply. We need to note that carrier, ring gear, and sun gear all rotate about consequent axes. Planetary drivers may have 1, 2, or 3 stages. Each stage of planetary drivers have the 2 degrees of freedom. The angular motion of 2 axes must be specific. Each stage between the third angular motion can be determined. Very high velocity reductions can be achieved with planetary drivers connected in series. This video shows 3 examples. The first example A involves combo planetary gears. This also permits the ring gear shown in that example to be replaced by another sun gear. In the second example B, the carrier can involve several shifts containing 4 or more planetary gears for greater reductions. The third example C is possible to connect planetary gears in series. When planetary gears are connected in series, very high gear reductions are possible. The most common planetary driver is the differential in rear-wheel driven vehicles. This picture shows you a hyper gear set and the differential bell gears used in a 2-speed rear driven module as part of an all-wheel driven powertrain for a 2015 SUV. Planetary gear trains are commonly analyzed using either the equation method or the tabular method. We only talk about the equation method in this course. In the equation method, the procedure is to write relative velocity equations relative to the frame for each of the gears with fixed rotation axis. Then we rewrite relative velocity equations for the same gears but relative to the carrier like this. If the angular velocities of two of the shifts are given, the procedure will always yield enough equation to solve for the angular velocity of all of the members in the gear system. If we stay with the carrier, all the gears will rotate like they are in the normal gear trains. So we can define the equation to solve the speeds of the gears. From these relative velocity equations, we have angular velocity of the gear relative to the carrier. Omega IC is equal to omega I minus omega C, where omega I and omega C are angular velocities of the gears and the carrier relative to the frame. From this figure, if the carrier is fixed, gears 2 and 3 will rotate like they are in the simple gear trains. If the tooth numbers of gears 2 and 3 are 20 and 40, we have the gear ratio relative to carrier is equal to -2. Here the gear ratio is negative because the external gears have opposite direction of rotation. We have three angular velocity, omega 2, omega 3, and omega c in this equation. If tooth numbers of gear 2 and 3 are known, and two angular velocities are given, we can determine the third angular velocity. Therefore, each stage of the planetary gear train has 2 degrees of freedom. This example is to find an equation that involves the angular velocity omega 2, omega 4, and the tooth numbers for the individual gears, where the sun gear is as member 2, the planet gear is as member 3, and the ring gear is as member 4. There are two gears 2 and 4 that rotate about fixed axes in the system, and we can use the relative angular velocity to determine their angular velocity. Omega 2 is equal to omega 2c plus omega c, and omega 4 is equal to omega 4c plus omega c. If we make the carry the reference link, the gears will move like an ordinary gear train, in which the planet gear acts as an idle gear. Therefore, we can compute the velocity ratio relative to the carrier as minus n4 divided by n2. This ratio is negative because the directions of rotation of gears 2 and 4 are opposite. We solve this equation for omega 2c and omega 4c like this. Now, divide the equation 13.20 by 13.21. We can get the result equation like this. This equation gives the relationship for the velocities of the ships coming from the gear train. So, given any two of angular velocity, the third can be determined. It is important to identify the direction of the angular velocities with a plus or minus sign. Typically, we can select counterclockwise as plus and clockwise as a minus. This example is to find the magnitude and the direction of the angular velocity of gear 2. Two numbers of gears in the gear trains are given in parentheses. Assume that the carrier and the gear 5 are driven clockwise at 150 and 15 rpm, respectively. There are two gears 2 and 5 that rotate about fixed axis in the system. And we can write the angular velocity relationship for these gears using the train rule for angular velocities. The equations are like this. And the angular velocity ratio of gears 2 and 5 relative to the carrier. Because gears 2 and 5 have the same direction of rotation, so the ratio is positive. We have the angular velocity ratio of gears 2 and 5 relative to the carrier. Assuming counterclockwise as positive, from the problem statement, the angular velocity omega c is equal to minus 150 rpm, and the omega 5 is equal to minus 15 rpm. The two numbers are given in the figure. Substituting the known values into the angular velocity ratio equation, we can get omega 2 equal to minus 13.95 rpm. Therefore, the angular velocity of gear 2 is 30.95 rpm in the clockwise direction. This example to find the magnitude and the direction of angular velocity of gear 5. Two numbers of gears in the gear train are given in the parentheses. Assume that gear 2 are driven at a speed of 16 rpm in the counterclockwise, viewed from the right end. Gear 4 matches with a fixed ring gear 6 and with gear 5 as shown in this figure. There are three gears 2, 5, and 6. They can rotate about fixed axis in the system, and we can write relative velocity equations for all the gears that have shapes that can rotate in fixed barriers. They are omega 2c is equal to omega 2 minus omega c. Omega 5c is equal to omega 5 minus omega c. And omega 6c is equal to omega 6 minus omega c. We can get the angular velocity ratio of gears 2 and 5 relative to the carrier is this equation. Because gears 2 and 5 have the same direction of rotation, the ratio is positive. And the angular velocity ratio of gears 2 and 6 relative to the carrier is in this equation. Because gear 2 and 6 have the opposite directions of rotation, the ratio is negative. From the problem statement, we know that omega 2 is equal to 16 rpm, and the ring gear 6 is fixed to the frame, so omega 6 is 0. The tooth numbers are given in the figure. Substituting the known values into the angular velocity ratio equation 13.35. We can get the ratio equal to minus 4.5238. From the equation, we can get the angular velocity of carrier omega c equal to 10.86 rpm. And given omega 2 and omega c, we can solve equation 13 and 0.34 for omega 5, substituting the known values into the equation. We can get omega 5 equal to 25.14 rpm. Omega 5 is rotating counterclockwise when viewed from the right. A two-stage planetary gear drive is represented in this figure. Gear 2 is the input member and the carrier 7 is output member. Gear 4 is a ring gear and is fixed. The carrier of the first stage is part of member 6, and it is rigidly connected to gear 6 that drives the second stage. This example is to determine the velocity ratio of the two-stage gear train. Tooth numbers of gears in the gear train are given in the parentheses. In this case, we analyze the first stage first. There are 3 gears, 2, 4, and 6. They can rotate about fixed axis in the system. Again, we can write relative velocity equations for all the gears that have shifts that can rotate in fixed barriers. They are omega 26 is equal to omega 2 minus omega 6, and omega 46 is equal to omega 4 minus omega 6. We can get the angular velocity ratio of gear 2 and 4 relative to the carrier 6 is this equation. Because gear 2 and 4 have the opposite directions of rotation, the ratio is negative. Because omega 4 is equal to 0, we can get omega 2 is a function of omega 6. Now, we analyze the second stage. There are 3 gears, 4, 6, and 7 that can rotate about fixed axis in the system. We can write relative velocity equations for all the gears that have the shifts that can rotate in fixed barriers. They are omega 6, 7 is equal to omega 6 minus omega 7. And omega 4, 7 is equal to omega 4 minus omega 7. We can get the angular velocity ratio of the gears 6 and 4 relative to the carrier 7 is this equation. Because gears 6 and 4 have the opposite directions of rotation, the ratio is negative. Again, omega 4 is equal to 0. The equation 13.44 can be rewritten for omega 7 as a function of omega 6. Combining equations 13.45 and 13.40 and substituting the known tooth numbers given, we can get the gear ratio of gears 2 and 7 equal to 68.06. All gears 2 and 7 both rotate in the same direction. In this example, the tooth numbers of the planetary gears do not affect the velocity ratio, but they will have an impact on the size of gearbox. In this example, we will analyze an example with bevel gears. The gear train is shown in this figure. The input to the gear train is gear 2 and the output is gear 6. The carry is member 3 that rotates freely about the shaft on gear 6. Also, the compact planetary gears 4 and 5 rotate about the axis of the carrier. Gear 7 is fixed to the frame. Assume that gear 2 rotates with an angular velocity of 100 rpm in the counterclockwise direction viewed from the right end. This problem is to find the angular velocity of gear 6. Even though bevel gears are involved, we can analyze this problem using the same wheel that was used for parallel shift gears. There are 3 gears, 2, 6, and 7, that can rotate about fixed axis in this system. Again, we can write relative velocity equations for all the gears that have shifts that can rotate in fixed barriers. They are omega 2, 3 is equal to omega 2 minus omega 3. Omega 6, 3 is equal to omega 6 minus omega 3. And omega 7, 3 is equal to omega 7 minus omega 3. We can get the angular velocity ratio of the gears 2 and 6 relative to the carrier like this equation. Because gears 2 and 6 have opposite directions of rotation, the ratio is negative. And we can get the angular velocity ratio of gears 2 and 7 relative to the carrier like this equation. Because gears 2 and 7 have opposite directions of rotation, the ratio is negative 2. In this case, we must determine the direction by inspection. This will show that if the carrier is fixed and the motion is inverted, so that all the other links and the gears can move relative to the carrier. We have gear 2 that moves in the counterclockwise direction viewed from the right end. Gears 2 and 6 will move in opposite directions. Similarly, gears 2 and 7 also move in opposite directions relative to the carrier. From the problem statement, we know that omega 2 is equal to 100 rpm, and the gear 7 is fixed to the frame, so omega 7 is 0. The tooth numbers are given in the figure. Substituting the known values into the angular velocity ratio equation, 13.51, we can get the velocity ratio of gears 2 and 7 relative to the carrier is minus 3.8. Then we can get the angular velocities of carrier omega 3 equal to 20.83 rpm. Given omega 2 and omega 3, we can solve equation 13.52 for omega 6. Substituting the known values to the equation 13.52, we can get the velocity ratio of gears 2 and 6 relative to the carrier is minus 4.083. Omega 6 is 1.444 rpm. The value is positive, so omega 6 is rotating in the same direction as omega 2. Therefore, omega 6 is rotating counterclockwise when viewed from the right end. This video shows you how this gear trend works.